All right, sorry.
All right. Hi everyone, welcome to our 6th Micromouse lecture on the Floodfill algorithm. Please scan the QR code if you haven't already. This is also our last lecture of the year, yay. And we're going to be asking questions throughout this lecture, and if you participate, you guys will get a reward at the end. True. Oh wait. Wait, okay, so here's a quick overview of what we'll be going over today. So we're going to be talking about maze solving. So that first consists of the maze design. So we're going to be talking about like the actual maze that we'll be using in competition, like the specifications for it, like its dimensions, where you're starting, where you're ending. And then we're going to be going over several maze solving algorithms that you guys might have seen or even used before, like in the fall rap competition if you guys participated. And then we're finally going to go into the actual maze solving algorithm that we will be implementing in our Micromouse. And that is the Floodfill algorithm. So we're going to be talking about how it essentially works and high level principles of it using pseudocode. Afterwards, we'll go into a demonstration of it where you guys can work through like the problems with it. And then afterwards, we're going to be talking about how to implement this in code.
All right. Now I'm going to start talking about that maze solving part that you just mentioned. So, one sec. All right, so this is the maze that you're going to have to solve in a competition. Like, well, it's not this exact maze, but this is like an example maze. The maze is 16 by 16 cells, each of which are 18 centimeters by 18 centimeters. So it's like actually really large. It's like 3 times, well, roughly 9 times, but greater than 9 times larger than the rat one inside of the lab. So that's an area, by the way. So it's huge. And it's gonna like cover like a giant area on the floor, and like you can't place it at any point because it's so big. You're always gonna start in the bottom left corner, although it doesn't really matter. I guess it's kind of like a weird distinction, but anywhere, if you orient the maze in any way, if you're facing up in the bottom left corner, that's a legitimate start. So this is an example. You could also technically start here, facing this way, or up there, facing down this way. And anyways, you get it. You're always going to start here. So these are like things, by the way, I'm telling you things which you always know are true, which is important for your implementation because it would be a lot harder if you didn't know these things, like where you started or how big the maze was. And then the goal is always going to be in the center of the maze, which is these four cells in total. It's always there, and if you enter any of them, you've solved the maze. So. And then it says we need to navigate with no prior knowledge, but like this is like the knowledge you have beforehand. This is the only knowledge you have. I guess you also know that there are all walls all on the outside, so you also know that, I guess.
And then wait, also like to add, right when you start, there's always going to be a wall to the right of you, so
that's
you can assume that too. So you know the dimensions, where the goal is, and like when you start, there's a wall to your right. That's like all the knowledge you have.
All right.
Okay, yeah. So here are 2 basic maze solving algorithms. The first one is dead reckoning, and the second one is wall following. For the fall rap competition, I think in previous years they used dead reckoning. Did we use it?
Yeah, they used
okay, yeah, you guys probably used dead reckoning too for this year. This one is basically have your Micromouse move straight until you hit a wall, in which case you can't, then you turn and then you go in a straight line until you hit a wall again and then repeat. Whereas wall following, like the name suggests, either follow the left wall or the right wall, but there's some complications with that. So dead reckoning, it only works for paths that aren't branched mazes. Yeah, and then what I mean by this is, so dead reckoning, you only go straight until you hit a wall, but on that straightaway, if there are like left or right turns that you can make, the mouse actually won't make those turns, and say you need one of those turns to solve the maze, you just won't ever be able to solve the maze. You just continues to go straight. Whereas the wall follower, it only works for simply connected mazes, and this means that like, say like you're following the right wall like infinitely, like you continuously follow the right wall. A lot of mazes, it's like it has loops. That means that like if you continuously follow the right or left wall, you'll end up back where you started, in which case it forms a loop. So like,
so simply it's not simply connected because there's like these free areas here. You see that? That if it was simply connected it means the entire maze is like connected, or it's made of two fully like connected things. But in ours, it's made of many different things. So if you actually follow this entire wall of this maze, anyways, it's kind of a complicated path, but you would realize you would actually just end up all the way back to the start again, and you wouldn't actually make it anywhere here because of these like floating areas which you need to be able to navigate. So like there's an example of one. This is an example of one. That whole area, anyways. This is how it's not simply connected, so you can't just follow the wall.
Yeah. And for the purposes of the Micromouse competition, every year the mazes are different, but they're designed where Dead Reckoning or the Wall Follower won't work at all. So that's why we don't use it. Another maze solving algorithm which you guys could use is random. So at each intersection, you basically choose randomly which direction to go. This is like pure RNG, and it's very inefficient, and it would take a very long time to find the goal. So theoretically, at the All-American Micromouse competition, if you were to use this, it would be really cool if you were able to solve it, but in most cases, you just like surpass the amount of time allotted and you wouldn't be able to solve it. But it could work. Another maze solving algorithm is Tremo's algorithm. This is like a depth first search, I think, and it basically marks the paths you've visited, and it prefers the unvisited ones. So it would go sequentially, like through like all of the paths in the maze, and once it finds the goal, it'll just find the goal and you're able to solve it. But it doesn't guarantee that it's the shortest path since it's doing sequentially, which is why we actually use the Floodfill algorithm. And this algorithm guarantees the shortest path after several turns, in which we'll go over in like the next few slides.
All right, so now we're gonna go over the actual Floodfill algorithm. We're gonna adjust everything. Man, these animations are kind of annoying. All right, so the high-level idea, as you can see with this Minecraft water here, is we're trying to find the path between the start and end point of the maze, and you can imagine that, or the way that the Floodfill algorithm works is simply like trying to pour water into the maze, starting at the goal we want, and then we see, or you can do the goal or the start. You do either of those, and whichever path water gets to the goal first, that's what we know the shortest path is. It doesn't work with like real life water because real life water has like inertia and stuff. But like with this Minecraft water, you can see like to get, for example, say our goal was here. You can see like the fastest path was here to here to here, because that every time. What am I saying? That was this is the water that got here first, and so that's the shortest path.
Oh wait, this slide is really hard to understand, but this is why they call it like Floodfill, I guess. Wait, don't worry if you don't understand it yet, but essentially, since you know where the goal is, you like how they always like put an analogy for Floodfill is like you basically just pour water on your goal, which is this center, and say you were starting at this corner. How water would flow is basically like the shortest path, which is why it's like the most optimized path. Don't worry if this doesn't make sense yet. Like, yeah. This slide is, it's just like an introduction. Don't worry.
So, also, I mean, let me start next
yeah,
slide.
Sloki is really hard to explain things like that.
Well, it's hard to explain without knowing the whole thing first.
Yeah.
So, as you saw with the Minecraft water can only like travel up and down and left and right instead of like every direction like real life water can, which is also like your mouse. So you can see here, real life water might travel in these diagonals, which your mouse can't do. So instead, we use what are called Manhattan distances or paths or whatever you want to call them, which is basically just like the distance that would take if you only moved left or right. There's also other ways you can think about it here, which is like the number of moves to get to the goal from a given cell. So I think the Manhattan distance from this cell would be like 9 because it takes 9 moves to get all the way to that top right cell. In the Floodfill algorithm, we move towards cells which have smaller Manhattan distances because that means that we're getting closer to our goal, because that means that cell has fewer moves to get to the goal. Also, the name of this comes from like like a city like Manhattan, or it tries to imagine it as like a city like Manhattan where like there's a bunch of like crossroads and you can't really like walk through buildings and stuff. You have to like follow the grid of streets and stuff like that.
Oh, I look, you didn't know that. That's pretty cool. Oh wait. Also wait. I'll explain this diagram here. So like what the Floodfill algorithm in your Micromouse will actually do is like in your mouse's memory, it'll have like a representation of the maze, kind of something like this, but in terms of like arrays or some way to store it. And in which case, these are all the Manhattan distances. Say this is the goal. A Manhattan distance of like, notice that like it's 1 away from the goal, 2 away from the goal, 3 away from the goal. So those are Manhattan distances. And say you were to start here, and this is your goal. You basically follow the shortest Manhattan distances from like 9, 8, 7, 6, 5, 4, 3, 2, 1. So like 7 here represents like 7 cells away from the goal, and so forth. Does that make sense? Do you guys have any questions?
Okay. Who was that?
Oh, my bad.
Yeah. So like yeah, if you pour the water on X and you go and move up, down, left, or right, you can see after 1 move it's up there. After 2 moves it's either left or right. After 3 it's either there, or there. Anyways, it keeps going all the way through the whole maze, and you only list the smallest one. So like technically the water is going to follow path here, 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 back to here. But if we already reached that just by going here to here in 3 moves, so we're not going to list that again because we already know a shorter path, which is this way. We're not going to list like what? I don't know, something greater than 10 probably. Where's my mouse, bro? It's on this screen?
It's up there, yeah, it's on that screen.
Okay.
Okay, so now I'll be going over like the general algorithm for what we'll be doing. So first things first is you want to assume that the maze has no walls to start with. And this is because when you start off your mouse inside the maze, your mouse has no idea where any of the walls are in the maze, right? So you first start with no walls, and then you use Floodfill, which is the algorithm to basically populate all of the Manhattan distances inside your maze on your Micromouse's memory. And you basically calculate all of the initial Manhattan distances. So like on your mouse's memory, it'll look something like this. So without any walls, right? There's many different paths to get to the goal. So the goal's here, say you're here. You can either go like this route, as long as it's decreasing, right? So the second step is you want to travel towards the decreasing numbers. That way you'll guarantee yourself moving towards the actual goal. And ideally it will give you the most optimized path. And as you're traveling through the maze, you want to update your internal map as you encounter more walls. So as you see the walls, you kind of want to document that, in which you'll store it inside like the memory of your mouse. And if you ever get stuck, where you're surrounded by walls and like larger numbers, you want to recalculate Floodfill and get new Manhattan distances using the discovered walls you have to get a new optimized path. So this sentence kind of is like same thing. Basically, you want to resimulate you want to recalculate the Manhattan distances every time you get stuck. That way you can get the most optimized path. We'll go over an example like after the slide in case this doesn't.
Does this one make sense? Like why this grid is labeled this way? Like we basically blue is unknown, and we just like poured water down here, and then all of these were just based on how many moves it took the water to get from to each of these cells. So like it only took 1 to get to here, and it took 2 to get to here, it took 3 to get to here, it took 4 to get to here. So that's basically how those are calculated. But once we figure out where walls are, then things will change. Also,
yeah.
How do you node walls, like in your code?
how do you what?
How do you like mark a wall in your code?
You'll have to do that yourself. I don't know. What do you mean? Are you mean like
store the walls?
how do you store it, or like how do you know there's a wall?
How do you store it?
Oh, you'll just have to make like an array or something to represent the maze and represent walls and stuff like that. That's what you'll have to do. Two-dimensional array or something like that.
Okay.
Yeah. There's many ways you can do it, but that's probably the simplest. Like I think what you can usually do is just have a 2D array, and then like for each cell, I don't know, you can have like a struct, or you can have like a bitmap if you know what that is, or bit string, and then just like a struct in that thing tells you if there's a wall on top, to the left, to the right, or to the bottom.
And like when you do implement this, oh wait, I'll get into that later actually.
Yeah. I think we're gonna go over
an
this
example of
example.
this. So, okay, so we're gonna go over this example really quickly. So, the triangle dictates where your mouse is actually, where your mouse actually is, and on the starting point, you know, like
do it.
there's a wall to your right.
Have one and like do it.
Oh wait, should we have this one or they did it on the next
Well,
one?
they can just show what happens. Like they can just say what happens.
I think we should just go over this one.
Okay,
This
sure,
one.
sure.
Yeah, yeah. Okay, so basically the triangle dictates where your mouse is, and initially, right, you don't know where any of the walls are, so it populates all of the Manhattan distances using Floodfill. So it's gonna go towards like decreasing numbers, right? So it'll of course go to number 3, so press it. So there, it goes towards number 3 in decreasing order, but as it travels through the maze, it'll document the walls. So right when you're here, you already know where 2 walls are. You passed one of them, and this is a new one, right? So afterwards, you're gonna continue going into decreasing numbers of Manhattan distances. So go again. So then you go to 2, and then what does it do? As you move along, you document more and more walls. So it'll document this wall inside your Micromouse's memory. But this wall technically doesn't really do anything because it's not like you were trying to go to an increasing Manhattan distance. You're still going like 4, 3, 2, 1 into like decreasing order. So it doesn't really do anything, although it's good to know that that wall is there. And then go again. Okay, but now as you're going to the 1 spot, you see a wall in front of you. And now your mouse is considered stuck. It's only stuck when you can't go to a decreasing Manhattan distance. So it's trying to access this 0 cell right here, right, the goal, but then there's a wall. So what does it have to do? It has to recalculate the Manhattan distances with all of these discovered walls using like the Floodfill algorithm. So go to the next slide. And then this is what it will look like once you use Floodfill and recalculate the Manhattan distances. So notice how like after you see this wall, use Floodfill and it'll re-update like all of the Manhattan distances, and you're gonna basically repeat this like operation and keep going until you get the cell. So like next up, you would go like here and then to the goal. But if it gets stuck again, then you'll have to do it again.
Yeah, I mean, yeah, makes sense. Although it really like recalculate here because you only know 1 wall.
Yeah.
Or like 1 significant wall, but you can still see like how it works. And then before we said like this cell was 1 Manhattan distance away, but then we're like, oh, we realized that was actually wrong. And based on what we know now, it's actually 3 Manhattan distances or cells, whatever you want to say, like 1, 2, 3. So these updated for right now, and now it's no longer stuck because 3 is greater than 2, and so we have shorter paths to go visit now.
Do you guys have any questions? Yeah.
How do you pick between the 2 paths?
You just arbitrary.
Yeah.
Usually your thing will just like, whichever conditional comes first, that's what will happen. Like,
But it doesn't matter.
it could matter actually in the maze, like, but you can't.
Like,
You don't know that, yeah.
So,
Okay.
like last year, sorry, let me finish. Last year, there was a branch of the maze where like if your thing biased going left instead of right, it would take like way longer for you, and mine didn't, so it took shorter.
But then you could also like, to like solve this problem, you could have like a button on your mouse that like, you know, prefers left or prefers right, and you're allowed to actually like.
You could do that if you
Yeah.
really wanted
Yeah,
to,
yeah,
but
you
you really don't need to. If your mouse is like robust enough, it will find the shortest path, and then it won't matter. Okay, what's your question?
So we're able to actually tell the mouse where the center of the maze is, or
Yeah.
what the goal is?
That's right.
Always in the center.
And then when you say your mouse is robust enough, what do you mean by that? Like they will just try a bunch of different paths?
Do you remember at the start you said that if you given enough runs, you'll get the shortest path?
Yeah, of course.
Like so, on first pass, we'll see this later maybe. I don't know if we will see it later, but on your first run, by the way, as long as the maze is solvable, you will get to the goal with Floodfill. But it's not guaranteed that on the first run it will be the shortest path because of like mistakes it might make when it doesn't know as many things. But given many runs back and forth between the start, it will approach the best path, and usually it's within like 1 or like 4 runs or something like that, and so it's not that much. And that's what I mean by it won't matter if there's a bias anymore because it will have found the shortest path. You go ahead. Sorry.
Well, like you said, like if it forks and goes around and comes back, and one fork is gonna be faster than the other.
Mm-hmm.
If it finds a fork and it gets really efficient at this fork, how is it then gonna go and try that other one?
Because
Why would it
what will
go try
happen
it?
is like, so it's hard to explain, but like, so let's imagine like it goes this way and like you can't see the walls here right now, but like, let's say the path ends up being like this, and then this, and then this, and then this. But then we're right here, and say, I don't know, let's just say it follows the same path back, which it probably won't, but if this is like fully enclosed, but anyways, it follows the same path all the way back to the start, and then we go again, and we come here, but we realize something, we actually haven't like seen anything up here. This Manhattan distance is still 2, which is gonna be less than whatever this is down here. Does that make sense why that is? Like, if the actual path that we have to take was this, it's like 1, 2, 3,
Oh,
4,
yeah,
5,
that
6,
makes
7,
sense.
8, 9 Manhattan distances or away. Whereas, or cells away, I should stop saying Manhattan distances away. Whereas we see here, we still have this marked as 2, we should just go there, because it looks like it'll be shorter. We might end up realizing it's not shorter, and like, actually this is fully blocked off, and so what might happen is it goes, visits all of these, and then like, gets here, it's like totally dead end, it's like, well, now I gotta go back. It'll go back all the way through your thing, and by then it will have found the shortest path, which is going through here and then down here.
That makes sense, thank you.
David, you got a question?
How many attempts do we get at the actual thing?
You get 5 attempts, right?
I don't remember.
I'm pretty sure it's 5, yeah.
And like you could like save the memory.
Yeah. Also, you can just have it run back and forth over and over. Like you don't need to take your mouse out and stop it and do things unless you want to.
Yeah.
Like you can just have it. What I did actually was I just had it go. I don't know. It would be like go to the center, but then it was like okay, I solved it, but then I just set the goal back to the start. And then I would just go back to the start. And then by the time I made it back, I found like the best route, or like maybe one more, and then I found the best route.
I'm not sure if I'm right, but I think you have like, you have 5 runs, and for each run,
I think you have more. I think it was like 7 or something.
Really?
Like 10.
I'm pretty sure you have 5 runs, could be wrong, but each run is stopped after your micromouse either stops moving or like after 10 minutes has passed.
Well, actually, it's called. It's not until it stops, until you take it out. It's like, you could theoretically leave it there all 10 minutes and it doesn't work, but it's not gonna solve it, so you might as well take it out and try something different. Wait. Just take a good look, let me check it out, bro.
What?
Wait, I can go to the next slide though. Or is it mine?
Oh wait, I'll talk more about this, or, wait, you go back to the past slide, let's talk about it a little bit more. So, how do you actually store like, so eventually you're gonna have to represent this in your memory, right? So how do you actually represent that in C? Each cell is actually gonna be like a struct. Have you guys learned what structs are yet?
Yeah, shut up.
Okay, but struct is basically kind of like an object, so it basically, you'll have like a Manhattan distance, and for every cell, you'll have a Manhattan distance for that cell, and you'll also probably have like the coordinates for that cell. I think that's what most people store it as, but we'll talk about this more later. Are you able to find it?
It might not even say, bro. Well, 8 runs.
Oh, 8 runs? Oh, my bad. Is it 10 minutes? Either 10 minutes.
It actually, apparently it's based on the rules, like it can change, but I think it was like 8 or something. Anyways, it's like significant.
Yeah.
Okay.
Okay.
This is mine.
Yeah, it's you.
Okay, so I guess here's some. Oh my god, it's not a deal. Here we're gonna get into like the pseudocode of how the Floodfill algorithm actually works. So right now, you should understand like at a high level what's going on. Like you go into your stock, you refill with the correct distances or more correct distances. You keep going with your stock, and then eventually you'll make it to the center. So how we're actually gonna, by the way, so when we talk about Floodfill right now, we're talking about just the calculated distances. Because that's actually what matters. Like it's easy to just, once you have those, it's easy to just tell your mouse, go to one of the cells which is a smaller distance away, and then that's trivial. But this is what matters. So what we're gonna do to implement the Floodfill algorithm is we're gonna initially set all of our cells, except the goal cells, to like a blank state. So they're not gonna have any distances on them. In actuality, you could just set them to like -1 or like some really large number or something. Well, we know the goal cells are 0. They're 0 cells away from the goal cells. So we can start with those ones. And then once we've set those to have a distance of 0, we're gonna add them to a queue. It's not like it's CS32, but basically what a queue is it's like a data structure which you put something in. When you put something in, when you take things out of it, it's
First in,
it's first in, first out. So whatever you put in first will be the first thing you take out of it, basically. So here's an example of that. We put in 1 first, and then we put in 2, and then we're like, let's take something out. Well, 1 will be taken out first because that's the first thing we put in. And so it's basically like a line in real life. Like if you're waiting in a line, the first people in line get served first or something like that.
Yeah, we'll go over like why we actually use a queue,
Yeah.
but yeah, this is like the general way.
So once we set those cells to have the value of 0, we're gonna add them to our queue. The order doesn't matter, we're just gonna add them. And then once we've done that, we can start like this, our like main loop of what we're actually gonna do, which is that we're gonna take
As long as it's
the front cell out of the queue, which right now is one of those goal cells. And then we're going to set all of the blank and accessible neighbors to that cell's value plus 1. So by that I mean like we're gonna look at all the neighboring cells of that cell, and we're gonna say, okay, is this one blank, as in it hasn't been assigned yet a value, and is it accessible? Is there not a wall blocking our way? And if those 2 conditions are met, then we're gonna set that cell's value to the value of that other cell plus 1, which is basically just saying like, oh, this cell is just 1 distance away from here. Does that make sense? Once we do that, once we set all of the neighboring cells values or the appropriate cells values to that value plus 1, we're gonna add those cells that we just modified their value to our queue again. And then we're also, by the way, when we analyze this thing at the start of the queue, we're taking it out of the queue, so it's no longer in the queue anymore.
Basically, to like restate, you're gonna start off with your goal cell, and you're gonna put that into the queue, and on every loop, you're gonna like basically remove like the cell at the top of the queue, and then all of its neighboring cells you're gonna add back into the queue, and then the process
all the correct, all those that are,
all the available ones.
yeah.
And then the process will just kind of repeat, but then like the main thing is to set the cell's value to +1, right? Because your goal is 0, but then every cell branching out from it is just gonna be like +1, +2, +3, and so forth.
And you do this until every cell is, well, actually you do this until the queue is empty, which will happen when every cell has been assigned a value.
Don't worry if this doesn't make sense, but like we're gonna go over a
Yeah,
demonstration.
we're gonna
right
do
next
that
one.
now, so.
Okay. Do you wanna take?
I guess it's supposed to be me, I guess. Okay, so this is just the same thing we've seen above. Wait, no, we're supposed to demo this, right?
Yeah,
Or like,
yeah.
they do it or something?
Uh-huh.
Okay, now we're
Or
gonna,
we could start it off. We could
Okay,
first
well-
do it,
we'll start off, I guess, this one.
Yeah.
Let's move this up. So this is our queue on the bottom, by the way. Okay, it's kind of covered though. Okay, so by the way, this is the front of our queue and this is the back of our queue. The like idea is that we're putting things in through the back and then they filter all the way to the front until we take them out of the front. So when we put things in, they go in here and you'll see it like they build up like that, like a line. Okay, so when we first start, we've done what it says up here. We've set all the things to blank except for the goal cell, which is set to 0. We set it to 0, and now we're gonna add it to our queue. So we put it in through the back, and now it's right here.
You just dictate with the 0.
I'll put a nice thing there.
Okay.
All right, that's our cell right there.
Yeah.
And then now our algorithm tells us take the front cell of the queue out of the line, and let's do our calculations on it. All right, we're taking this out of the line.
Wait, just do an X so they see.
Okay, sure.
Yeah, I think.
Sure.
So you're gonna take it out of the queue, and then
We're taking it out of the queue, so it's not there anymore. We'll just leave it, I guess. And now we're analyzing all of the neighboring cells, which is this one, this one, this one, and this one. And we're seeing, are these blank? These are all blank. And are these all accessible? As far as we know, these are all accessible because we don't know any of these walls are here right now. So what we're gonna do is we're gonna set each of these values to the corresponding, or this value plus 1. So basically just 1, 1, 1, 1. And then we add all of these cells to our queue. And so 1, 1, 1. All right, 1. All right. So now this is what our state looks like right now. Do you think we should go over this whole thing? We can do like 2
no. And then no, I think that's enough. We should take them all 2 now.
All right, I guess now someone else want to show us what happens next. You raise his hand first. Sorry. This is super for hard exams.
Okay, wait, let's just say, also, wait, these are all different cells technically. Let's just call this like A, B,
Yeah, sure.
C, D. So let's have, okay, let's have this be A, B, C.
Yeah, in reality, in your code, these are like fully distinct structs.
Because they have like
They
different.
just have, they end up having the same value, but they all have different coordinates and stuff. All right, so show us what to do now.
So we're gonna go to the next, like the first one that's in the line.
Okay.
Yeah.
So we're just gonna
Yes.
take it out, and then that's like 1A, right?
Yeah.
Yes.
So this one, and we'll go to all the ones around it, and we'll mark them.
Well, tell us exactly that process right there. So we said we have these two criterias, and so it does have 4 neighbors, but show us why you're only gonna mark 3, which is probably what you're gonna do.
Because it has to be blank,
Yeah,
and this
so,
is not blank.
Yeah, yeah.
As a value, so you don't mark that one.
yeah, exactly.
Okay.
I was fishing out for that answer, but yeah, you're correct about that.
And the reason why you don't want to kind of override it, it's pretty self-explanatory. You don't want your goal to be like,
Well, no, it's because everything that's already on there is already
yeah,
the shortest
yeah, it's
possible.
already, yeah.
Yeah,
Nice.
that's right, then you add them to the queue.
Why do you draw a box on every single one?
Because it's cool. Nice.
Okay, thank you, thank
Anyways, so yeah, that was good. I'm gonna assume you already knew that you're gonna do that now for all of them.
Yeah.
And so yeah, you would analyze this one. These are both not blank, so not those. Then you do it for these ones, but those ones, and so I'm gonna just fill the rest of the thing out. It's fine. Or like,
I'm down. Or
Yeah.
should we take an example for like,
Well,
what's your 2?
no. I think it's fine.
Okay.
Yeah. So I'm not gonna fill it top. It's too far from me. But it's gonna end up looking something like this. Once we do the 2s, we're gonna analyze them. It's gonna be like, nope, not blank, blank and accessible, blank and accessible. All right, 3, 3, 3, 3. The same goes for these ones. And then for this one, the only blank and accessible one is right here. And so this is gonna be 4. 4. And by the way, this is symmetrical. That was the same on the top. I just don't want to reach it there.
Does this make sense?
Yeah, does this make sense of what we just did? Like why? So this is like literally what you have to implement. And this is gonna happen anytime you're stuck. Okay, so, all right, so, oh, I forgot. All right, so what I just drew is what is shown there. So what we just did is that exactly, which makes sense. Seems like it makes sense to all of you. So let's go and see if we can find oh yeah, here we go. So this is an example of where no longer our Manhattan distances are accurate to our knowledge. So even though, I just want to mention, even though we found new walls here when we were doing this, it wasn't like making our run worse. So we didn't technically need to recalculate the Manhattan distances. Because like, even though, so when I went to here originally, I technically could have gone here because it was marked as a 2. But even though this is no longer accurate, actually technically it's still accurate, but even though I can't go to this path anymore, I can still go to this one, so we don't even need to recalculate it. Although you can if you want. Like you can just recalculate every move, but yeah.
I'm just curious, like, can you set another parameter to like prefer like routes that take less turns? Because wouldn't that take you more time?
Yeah, you could do that. That would probably just, yeah, to do that. That's probably a good idea actually too.
Yeah, but basically, like what Michael's saying is like, you basically only need to recalculate, or you basically only need to do the flood fill, like once you get stuck. Otherwise, you can just keep going into like decreasing Manhattan distances. Yeah. Oh, do you know question? Yeah.
Okay, so now we're stuck here, and so let me see what the next slide is. Okay, and so now we're gonna restart our cycle. Well, I guess I'm not gonna start off the thing, but so someone else wanna come show us what's happening? What we're gonna do?
We're gonna be here for a while if you guys don't volunteer.
Yeah,
Thank
here
you,
we go.
thank you.
Like all I can say for now is that we made the whole thing blank and we set this to 0. But so what do we do after that?
So, yeah, I guess zeros in the queue.
Yeah,
Yeah.
yeah. So you imagine zeros in the queue
Yeah,
for
0
now.
to the queue.
Okay.
Okay. These are the only 3 accessible blocks.
Yeah.
Oh, you skipped a step.
Oh, I guess we should take this out the queue.
Yes.
True.
And then these are all 1,
And why is that?
because they're 0 plus 1, and they're all accessible and blank.
True.
Yeah.
Very
And
true.
we also add 3 ones.
Yeah.
And then I guess you
you could take out this one. But let's just say
Yeah.
this is like the bottom one.
Yeah.
Then, well, you would just do all the blank and accessible areas
Yeah.
to 2.
Yeah.
And then,
And then
alright, that's probably good now.
Yeah.
Don't worry.
So
Thank
on,
you.
so
Yeah,
forth.
that's
Yeah,
good,
yeah.
that's good, that's good. Good job.
Does everyone get what happened there? I think it seems like kind of trivial now, but like this is all you have to implement basically, and then it will work. Once you get this working, go on the shortest and the smaller number, and then you will solve the maze. All right, let's see. So yeah, it was correct. Oh, I guess we probably should have done this, but yeah, now this is instead of this being 2 or 1 earlier, it's now a 3 because we have to go here and then here to update this number. Okay. Like I feel like this example went on for a really long time. Oh yeah, I guess it is good to show that. So maybe we should.
Yeah. Wait,
Um,
this next up, right? I think it's wait. I feel like slide down the projector, or actually,
Yeah, I guess we can just go over it.
yeah, we can go over.
I don't even know. I guess
Okay. Wait, okay. I'll go over the next 2. So basically, right when you're stuck, right? We just recalculated the Manhattan distances. So this is our new loadout that we have in our Micromouse's memory. And what it's gonna do is now it's gonna go in decreasing order, right? So it's either gonna go bottom or it's gonna go top. In our case, for our scenario, it's gonna go up. So do that. So wait. Okay, so as it goes up, it'll go to this 2, and like it'll detect any walls and document them. So it sees that top wall and it'll document it. It sees the 3 walls in that one cell and it'll document that. And then finally, when it's trying to get into the goal cell, right, it sees a wall, and now it's officially stuck since it can't go to any other location.
Yeah, and so I don't think we need to do it yet. I think you guys understand, but basically now this is like a way more. Oh, I didn't change it. This is like a way more non-trivial case. It's going to be like this is 1, you know, 2, 3, 4, 5, and so now at this point we realize, oh, we were at 1 distance away, or 1 cell away. We're 5 cells away at this point, at minimum. And so I think when we update it, we'll see that. Yeah, and so it turns out we were totally wrong. And I don't know if this example goes all the way to finish. I think it does. Let's just see. So at that point, we recalculated. We're like, okay, let's go to our smaller numbers again. So we went here, here, here. And it looks like, oh yeah, so here we also run into an error because we thought before we could just go here and then turn here and then go in, but there's actually a wall here as well. And so
basically, whenever you're stuck, you want to recalculate your Floodfill to get new Manhattan distances, and it's always going to prefer decreasing Manhattan distances, so it'll just keep following that order.
So you see, yeah, we got stuck again because we thought once we got here we could just go up, but it turns out we can't. So we have to recalculate again. We recalculated. Oh wait, okay, let's just go right. We got stuck again because we realized we wanted to go up again and then just go here, but we can't do that. So we got to recalculate again. Oh, so we can just go right, and then it's all skipped because at that point we went right, you went here, and these were all accurate and stuff like that. If your thing tried to go up here, it might have tried to go up here and then go here. You would have realized you would have gotten stuck here, and then it probably would have gone back this way. And yeah.
Is there like an effective way to make sure we programmed it to calculate Manhattan distances correctly, or would it just be like the mouse isn't working, you probably didn't calculate them correctly? It's
Yeah,
like I can't really print it out. So.
On the assignment that we give you, there's like some random guy made like this really high fidelity Micromouse maze solving simulator, and so so he has like a built-in API that you're just gonna use, and it's gonna be like it'll like tell you if there's walls there or like stuff like that. And so you'll basically use your algorithm on that simulator, and you'll see if it works or not. You'll know if it doesn't work. And it has like tons of feedback. Like you can mark the Manhattan distances and stuff like that, and mark where you see walls and stuff like that. Does that make sense?
Mm-hmm.
In fact, I could probably just show you guys now. Might as well.
Yeah, might as well.
Actually, maybe not. I don't even know what it's called.
I don't know what it's called either. We pulled the assignment.
No, I got this. Do you guys have any other questions so far? I guess.
Everything makes sense, yeah.
How do you guys store the walls to like know this cell has a walk, would it be like a part of the struct for the cell? Or
Yes.
What?
Like how do you indicate that there's a wall?
There's a lot of ways.
Yeah.
But so the way I told you, the way I did it is like I basically just like stored a 4-bit. No, I just stored a 4-bit number. So like I stored a 4-bit number in like my 2-dimensional array. So I'm just gonna like this is my 2D array, by the way. So blah blah blah. Or I'll just draw it this way, I guess. Dot 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 dot, and then there's a whole grid. Does that make sense what I'm drawing here? These are all cells, but then I stored a 4-bit number, and so if like the first bit is 1, it means there's a wall on top. If it's 0, it means there's no wall on top. Does that make sense? If this one might have been left, if it's 1, there's a wall on the left. Otherwise, there's not. This is like there's a wall on the bottom, and then this is like there's a wall on the right. So this bit thing represents this configuration of a maze. Does that make sense how I'm doing that? You can also just make a struct and it's like bool wall right. Oh, you can use bool as in C. Like int wall right and then 0 1 or int wall left is 0 or 1 or something like that. Does that make sense? How it's happened? I gotta find this, bro. Bro, what's that guy's software called? Alright, we'll just keep going. Alright. So what is this?
Oh, I think, okay, this is just like a recap slide, but basically, now from your starting place, like once you do everything, no, just the wall.
I think what this is showing, I think what this might be showing, let's see. Oh, never mind.
That's funny.
Well, here's like, here, let me take this. Yeah, I don't know why this is here.
I mean, this is just like the finished product. Like you're from your beginning, you're able to get to the goal, and yeah.
So like, you guys saw the whole process of how like we got here earlier, right? So that one we solved it necessarily, like it has to solve it, but it doesn't have to be the right way. So say let me just move this up and I can like make modifications. But like, let's pretend that the path is like different for a second. A long time. So let's say instead of being able to go this way, I don't know. I had to go. So right now we went this. I'm not going to redo the walls. But let's say instead of that way, I had to go this way or something like that. I'm almost certain the algorithm would have still done this path because at this point, actually I'm not even going to explain that. But let's just say this was the actual path we needed to do. If you realize right here, this path is like let's see, 1 2 3 4, 1 2 3 4 5 6. So this one is like longer than the other path. And so at this point, if we had gone back to the start and then gone to here, this path would actually be a longer path than what we think we could do from up here. Does that make sense? Like we think if this is still 8 right here, this would be like something like 10. And so we're like, okay, maybe we should try this path. Even though it might end up being not accurate, we'd still try it because it's still less. Like the algorithm doesn't, once it finds a path, it doesn't stick to that path, it continues doing the same thing over and over. But then eventually you will find the correct path. I kind of just explained it badly, but I wish there was an example of that. But maybe if I get the simulator working, you guys will see. Because you'll see it will almost always on the first pass, it's not going to find the correct one. But then almost always after a few runs, it's going to find the correct one. And you'll just see, it will just go back and forth over and over between the same thing. I'll find it after. Alright. This is yours, you know? I don't think it's mine.
I think so. Yeah.
Alright, I think the queue concept wasn't that difficult, but basically queues are first in, first out, like we said. You enqueue them from the back, and then whichever one you enqueued first gets taken out first. These are some terms that you might use. Push is what is the term you use when you put something in the back of your queue. Pop is the term that's used usually when you take something out in front of your queue. And then I think we're going to go over like ways you can implement this, because in CS32 you're using C++, I think, and so like there's like a standard template queue, or you might have implemented it yourself too, I don't know. But in C, there's no standard template library, so you'll need to make your own queue.
So for implementing a queue is an abstract data type, so you can implement it like a lot of ways. Like Michael said, C doesn't have a standard library like C++. So in your CS32,
Yep.
you're able to just like import queue, right? But for Micromouse, you can't. So the two main ways that we actually implement a queue is using a circular array or a linked list. So also wait, instead of, you could also just find like, you could technically import a queue from like from someone's like from a library in C though.
Yeah, sure.
Like, yeah.
If you really want to, but I was just implement it. It's not that
Yeah.
hard to do. Also, we left you in the dark. You can get boba after.
Yeah.
That's your prize.
Hey, and the people who volunteered, you guys can pick your boba first.
Yeah, there you go. That's the prize. Okay. Here, I think, alright, so here's an example of a circular array. Let's do mine. I kind of don't like circular arrays, but basically the way circular arrays work is it's actually just a normal array. But you have these two indexes or pointers or iterators or whatever that show you where the start and the end of your array are. So right now, even though the start of our array is over here, like the start of our circular array is right here, and the end of our circular array points one past the end. That makes sense. And so I think that's all what that says. I think it's like going to be an example or something. So if we were to add, this slide's not helpful. I don't actually know what's going to happen.
No, yeah,
next.
you click.
I think so. If you add an item, you put the item at the end position, and then you move the end one over. Same goes again, but if your end points past the end of your array, then you go back to the start of your array. Does that make sense? The same goes again. If you pop something out of your queue, you move the start. You take this value out, or you don't even take it out. You just need to move the start index over, and then now it's as if only this stuff is in the array instead of this stuff. Does that make sense how this is working? So it's called circular because we're gonna keep, if you keep adding and removing stuff, like your start is gonna like move over and make loops over and over, if that makes sense. We'll see how that's gonna work. So yeah, we're continuing to pop stuff out. We're moving our start index over. Oh, man, they didn't even show any unique things? Okay. So like, you'll know your, actually I don't remember how they do this. Does anyone remember, you guys know how they distinguish between an empty circular array and a full one?
An empty and a
Yeah, so think about it. If you filled up all of the items in here,
The end of the start point.
yeah, the end and thing will point the same, but think about it also. What about if everything's empty? It also points the same thing, right? So I don't remember, there's a way you're supposed to do that.
Well, you just check if start is null pointer or not.
Huh? I mean, yeah, no, that's not necessarily, no, because the thing is that's not how you implement arrays. Most of the time, like, remember when I said you don't even need to take out this value? Because all you need to know is that this value doesn't matter. You don't need to actually change what's in here. Does that make sense? So this could be a fully valid pointer to something, if that makes sense. It doesn't have to be a null pointer. This doesn't have to be a null pointer or not, or anything like that. Anyways, there's a way you're supposed to know. You should look that up.
Oh wait, I'm pretty sure it's if your start and end like if you're setting up.
Yeah, but that's the same if they're empty.
No, like.
Wait. Oh shit, you might be
No,
right.
there's some like
Yeah.
thing. There's ways you can do it. Like one way is you track the length of your circular array, and so you'll know if the length is 0, it's empty. If the length is the maximum length, then it's full. That's one way you can know. I think there's a smarter way, but I don't remember what it is. Anyways, you guys get how circular arrays work. You could, the advantage, do we talk about the advantages? I don't think we do. The advantage of doing this is not that large. It's like, basically you save some space, because at any given point in time, you're not gonna fill, like, anyone know what 16 by 16 is?
256.
Is that correct?
Yeah, it's
So, technically, you might need 256 things in your queue at once, which you actually don't. Never at any point will there be 256 things in your array. And so, we can just use a circular array to like avoid worrying about that. Or like to save some space, sorry. We can use a circular array, and then we don't have to make like a super long array to worry about the maximum case or something like that. Does that make sense?
Yeah, since you're constantly like popping stuff in and out of, like pushing and popping stuff in and out of the queue, like max is like 256. The second way is through linked lists, my favorite data type. But basically, you have a head pointer, and this points to the start of your linked list, and it basically points towards a node. And a node has two components. It has its value, and it has a pointer connected to it where it points to another pointer. So say this is your queue. At like the front of it would be the head pointer, and then the back of it would be the null pointer, or like that node with the null pointer. And then say you would want to, in this case, what is it?
I think you're popping the value, right?
Pop. Yeah, you're popping a value, so you're basically taking it out and you're making the start point to the next node. And you can easily do this since the head pointer is pointing to, wait, go back. It's pointing to this node, and this next pointer is actually pointing to the next node. So you could just declare head pointer, like, point to the next point to this node's next pointer, and then, yeah.
I found the simulator, so I'll show that after.
Okay, yeah, we show that after. Yeah.
This is another example of popping it, I think, and then at that
Yeah.
point, it's pointing to a null pointer at the end, and so you know something.
Yep.
This is mine.
Yeah.
Okay. All right. This is such a way to, here was the things we were talking earlier. So you need something to keep track of your cells. You can use a struct to do this, where you just like keep track of the distance, and then like what track walls you have. That's it, honestly. It's all you need to track in that struct. So it's just like an easy struct with like a couple data members, and you'll just have a 2D array of those structs or something. You can also do it with like multiple 2D arrays as well, where like one 2D array has all the distances, and then one has all of the like left walls if you want to do each one for, and one has all the right walls, one has all the blah blah blah. Or you could just do it in the struct way, like I said. We don't have to worry about like performance that much, because all of our computations are like kind of very cheap, and so even if you do something super like cumbersome, it will still work.
Another tip is, you guys are probably familiar with C++ because of CS31 and 32, but here are like the most notable differences. There's no default constructor. There's no STL library. This is like because it's important for Micromouse since we can't actually like import a library to do our queue. We have to actually use a linked list or circular array. There's also no Boolean variable type, so you guys could, if you guys want to use a Boolean, you guys could probably just use like integer like 0 or 1. And overall, it's just not as fun, but we use it.
Not as fun. All right.
And then, and then these are some other tips. So here you can see like the other differences. So say you have a pointer in C++, you use new, whereas in C, you use malloc. And if you want to delete something, delete a pointer, I think in C++ you just do delete, whereas equivalent C code it's.
I haven't seen it live score.
I'm not sure, but I think it's malloc. It's free. There it is. Thank you.
All right.
And then, okay, final reminders. Final bill of materials and PCB design is due this Sunday. So if you got friends in Micromouse, tell them. We also have a work session this Friday again from like 3 to 6. And this is really early, but all American Micromouse competition, it's gonna be like week 9 Sunday or week 8 Sunday. It's Memorial Day weekend, and it's gonna be next quarter. Yep.
What time is it normally at?
In the morning,
Yeah.
like, I don't know.
It usually
8 a.m.,
ends by
10
3.
a.m. or
Yeah.
something.
8 a.m. is crazy. Do not do an 8 a.m.
I'm busy day.
Okay, we don't have any.
Yeah, there's no workshops.
Don't look at that.
Yeah.
Yeah, we had to leave that slide, bro.
Yeah.
Anyway, wait, let's show you guys the simulator, so you guys can see what I'm talking about.
No, we can put this like that. Oh yeah. That's
So here's like, this is what I was talking about, where's representation of maze. Red, I think, means like, I know there's a wall there, and then I don't remember what it shows. Let's just do it. Let's do it really slow at the start. Let's run this. So, probably the bottom left, like I said, is where we start. Yeah, so they're like grayed out when you don't know, and so you can see, you'll see when all the values update when I get stuck. They should have all updated there. Oh, no. They, only those ones did. Yeah. And so, this is how it's gonna actually work. Let me just show you it's sped up though, so you can see like, even once it gets there, it might come back in a different way. But then eventually after a couple runs, you'll see it's just gonna go in the same path over and over again. Let's watch that. I don't know where the mouse is, bro. Alright, let's go a little faster first. That it's solving the maze. It often looks like it doesn't know what it's doing, like for the first thing, but like it is doing the most optimal thing. But then if we go really fast, so I did just solve it there. If you guys saw that, if you see how it's not taking the same path over and over, it's kind of discovering new things. But I think at this point, it's discovered the fastest path. You see how it's just going the same path over and over now?
Yeah.
Whereas before it was taking different routes. Let me do it with a different maze because I think like there's like some. Let's use like a previous year.
Is there like an efficient way too to like once you kind of know the path, how to go faster through the straightaways? Or like, are we gonna be stopping?
You would
instances,
just do what he said and optimize for at least turns or something like that.
Yeah.
So
optimize for what?
at least
Like
turns.
these turns.
So you would have to figure out how to do it yourself. I've never done it, but it would probably just be like, actually it would depend on how you're doing
I
it.
just mean like to make it so it doesn't stop every single stop. Like is there a
Oh,
way
that is just you're gonna do that with your motor control
Oh,
stuff.
okay.
That's not with the algorithm.
Mm-hmm.
In like the
All right, let's run this
in
one.
like the verification video, you talk about like diagonal turns, like
That's hard to implement,
oh yeah.
but I mean you can try. And it's like you see how it went that really cumbersome way the first time, but I think it's found a better way. Oh, maybe it hasn't. Maybe that was the best way. Yeah, it was the best way. But I guess what I should have been highlighting was that when it was here, it thought it would find a faster way back down here, which is why it ended up discovering all this stuff, but then it realized, no, I can't find a faster way here, so let's just go for the top. And then now it's just doing the same thing over and over again, because it's found the fastest route. Or the shortest route, just the thing fastest. Shortest is not always fastest, but, well, because of, in actual optimizations, you want to make less turns, because turns take a long time, and so it might be a longer path that has less turns or something. Anyways, yeah, that's all I had to show you. But you can just get your boat by now.
Okay. Yeah, this concludes our lecture. Thank you guys. Yeah, get some boba. I got like 8 different types of flavors. I'll pick it up.